In this section, we'll be looking at principle of conservation of momentum. Because this section is quite long, I will split it into two portions. First part will be explaining what is principle of conservation of momentum. Second part will look at the different types of interaction or collision. For a system of interacting bodies, the total momentum of the bodies remain constant, provided no net external force act on the system. Or you can simply say the total momentum of a closed system is constant. When we say closed system, it means that there is no net external force. And this is a principle of conservation of momentum. Note, this principle is only applicable when there is no net external force, which means this is a closed system. We can say that the total momentum before the interaction or collision is equal to the total momentum after the interaction. But this is not good enough. What about during interaction? For momentum, it will be conserved during the interaction as well. In other words, in principle of conservation of momentum, when we say the total momentum of a closed system is constant, we refer to it before the interaction, during the interaction, as well as after the interaction. In the learning outcome G, you need to state the principle of conservation of momentum, so you need to memorize this. We'll watch a video to help you understand what is principle of conservation of momentum.
Conservation of momentum tells us that the total momentum in any closed system will remain the same all the time. And since momentum is equal to mass times velocity, even if you have multiple objects going at different speeds that might collide, for example, the total momentum of the system before and after the collision will remain constant. So for example, these two balls, which in this case happen to be of equal mass, whether one of them is moving and causes the other to move, or they're both moving and collide and move off in different directions, the total speed and the total mass of the entire system always remains the same. So for example, if this had a velocity of 0, and that had a velocity of 1, the first one might impart some of its momentum onto the second, but the total between the two remains the same. And that remains the same whether one remains still and the other comes to collide with it, or whether they're colliding with each other. It even works, in this case I put Velcro, it even works if these two stick together, the total momentum remains the same. So for example, if I can get these two to stick together while one is stationary and the other is moving towards it, once they stick together, the total momentum will remain the same, so the combined objects will have half the velocity of the one initially that was moving. Conservation of momentum makes it actually quite interesting and challenging to move around the ISS if you don't have something to reach onto a handhold. Because if you get trapped out in the middle, there's no wiggling you can do, no swimming you can do that will get you over to a handhold so that you can pull yourself to move through the station. Because no matter what I do here, if I just stay floating in the middle, I'm just going to remain here in the middle since the total momentum of the system has to remain constant.
Mathematically, the momentum before the collision equals to momentum after the collision, provided there is no net force. Do note that all these velocities quantity, they are vectors quantity. Therefore, the direction is important when you sub these values into the equation. We can verify principle of conservation of momentum using Newton's second law and Newton's third law. Remember, in Newton's third law, when body A acts a force on body B will act an equal and opposite force on body A, right? And we call these forces action and reaction pair. And in Newton's second law, we recall that F net is equals to change in momentum over time. If there is a net force, there will be a change in momentum. So a net force will always cause a momentum to change. Suppose we have two mass 1 m1 and m2, both moving to the right. If we take rightward as positive, total momentum before the collision will be m1u1 plus m2u2. During the collision, using Newton's third law, m1 exerts a force F12 on m2, and m2 exerts an equal but opposite force F21 on M1. We can say that F12 equals to negative F21 because the right is positive. Therefore, F21 is negative because it's pointing to the left. By Newton's second law, because Newton's second law will be change in momentum over change in time. If we substitute it for mass 2 and mass 1, you can form this equation. Since the time duration when they hit each other is the same, you can cancel delta t. And if we rearrange the equation, this is what we get. So you can see here, this is the initial momentum, initial velocity here. Here is final velocity, so this is final momentum, and this is initial momentum. Although in this formula, we use initial and final, we should note that the momentum is also conserved during the collision. Remember, the condition to apply principle of conservation momentum is that there is no net external force, or we can say that the system is a closed one. A typical force time graph of F12, as we've seen earlier, using the earlier example, is something like that, right? The force initially when they just touch each other, it is quite small. When they are pressing towards each other with the greatest force, that usually occur in the middle of the time. And then they begin to move away from each other. Therefore, the force exerted on each other is smaller. By Newton's third law, we know that F21 equals to negative F12. Since the force is negative, it should be shown below the x-axis. And we know that area under Ft graph, it is actually the impulse or change in momentum. From these two graphs, you can see that this is positive area and this is a negative area. Since area represents change in momentum, we can say that it is a gain in momentum, okay, for M2, and it is a loss in momentum for M1 because the area is negative. If the gain is equal to the loss, that means there is no change in the whole system. When we look at both of them as one system, there is no change in momentum. Since the total area, if we add up these two areas, it will be equals to 0. Therefore, the total momentum of the system remain constant. Right? Remember again, the condition is that there is no net external force. Now let's look at the steps when we want to solve a momentum question. First, identify all the objects that constitute the isolated system. Isolated system means there are no other force acting on it. Choose a sign convention for velocity or momentum. We say to the right is positive or to the left is positive. Find the total momentum before the interaction and find the total momentum after the interaction. Equate A and B to determine any unknown. In work example 12, we can see we have two trolleys, X and Y, and they are about to have a head-on collision. Okay, what does head-on collision means? Head-on collision means that they move along the same line, joining the center of masses before and after the collision. In other words, they will collide along the same line. So if they move towards each other in this direction in the beginning, subsequently, they will still move along the same line. Okay, it could be this direction or this direction, but it will be along the same line. Collision that's not head-on will be something like this. For example, this move towards here. After it hits this object, after collision, they move not along the same line. This will be a non-head-on collision. Okay, so head-on collision means they move along the same line before and after the collision. It does not mean that the object will move in opposite direction. They can still move in the same direction after collision. Okay, now let's look at the question again. So they have a head-on collision, meaning same line. The momentum of each trolley before the impact is given. So you can see this is a momentum before and the direction is given. After collision, trolley X reverse in direction, so it is moving in opposite direction. And momentum of X is 2. What is the momentum of trolley Y and what is the direction? So the key concept is this. First, we identify the body or the systems. So X and Y together, they should form the system. We must make sure that there is no net external force acting on the system. If there is net external force, then we cannot use principle of conservation of momentum. Since in the vertical direction, the weight and the normal reaction, they will cancel out in both cases for X and Y. There is no net force in the vertical direction. And in the horizontal direction, we must assume there is no friction, otherwise there will be an external force. Once we can make this assumption, we can apply principle of conservation of momentum, which means we can say the total momentum before the collision is equals to the total momentum after the collision. Step number 2, fix a direction. So we'll take rightward as positive. Step 3, find the total momentum before the collision. So before collision is using the m1u1 plus m2u2. Since the momentum is already given, you just use the number, but take note of the sign. Since rightward is positive, trolley Y is moving towards the left, therefore it is negative. Next step, find the total momentum after the collision. After collision, we know that X is moving to the left, so it is negative, and Y is an unknown. Last step, we equate the momentum before and after the collision, and from here we can find Py. Since Py is positive, it tells us that it is moving to the right. You should be able to solve these problems, and this is learning outcome H. We'll look at what is elastic and inelastic collision later on. Two bodies P and Q of equal mass traveling towards each other on a level frictionless track. Level means horizontal, and it's frictionless, telling us that there is no net force, no net external force. And the speed is given. At some instant during the collision, P is brought momentarily to rest, which means that the velocity is 0 at this time. What is the speed of Q at the same instant, right? So as we read the question just now, we already get the hint. Frictionless means no net external force, so we can use PCoM. In this case, we are finding the momentum during the collision. Compare it to before. And remember, conservation of momentum is applicable throughout before, during, and after collision. Another keyword, moving towards, means they are moving in opposite direction. So now we can solve the problem easily. Let's form the equation. Initial momentum of P and Q and the momentum during the collision. We know that during collision, Vp equals to 0, and we know that both P and Q have equal mass. Take positive direction as the direction of V, which means to the left now. We substitute in the values. Since P travel with a velocity u to the right, we call it negative u, and V is positive. Okay, for VQ, we just assume that it's moving to the left. If we are wrong, the sign will correct itself. Right, and since Vp is 0, we can sub in 0 into the equation. From here, we will find that Vq equals to V minus U, and that is option B. Take note that we reduce from level frictionless track to know that there is no net force. Therefore, P and Q should maintain their speed until they collide. Now let's check your grasp of concept. Suppose you are initially standing at rest and then you jump upwards, leaving the ground with a speed v. Obviously, your momentum is not conserved because your momentum before the jump was 0. Momentum is mv and v was 0 initially. And then when you begin to rise, you are moving, you have a velocity. So your momentum is mv. Is principle of conservation of momentum applicable in such a case? There are two solutions and they are both acceptable. Can you think of what are the two solutions? Pause the video. Okay, we'll first look at scenario B. A and B are both on page 18, but I will go through solution B first. Solution B, we have selected the system to consist of you and the Earth. Because you and the Earth is one system, there is no external force acting on you. Since there's no net external force acting on you, we can use principle of conservation of momentum. In this case, the push you give to the Earth and the force on you by Earth to push you off the ground. As you kick off the Earth push you upwards. So they are action and reaction pair. They are internal force since the system consists of both you and the Earth. So it is not something outside the system because it's acting on both of you. So as you jump upwards, the other body of this system is the Earth. It moves in opposite direction with a momentum of equal magnitude. In other words, if this is you and this is the Earth pushes you upwards and you have a V. Your mass is this. But the Earth has a very large mass and you push off the Earth with a very small v. However, this mv is equals to the mass of Earth times the velocity of the Earth. You should note that the speed of the Earth will be very, very small since the mass of Earth is very large. Right? That is why when you lift off the ground, you do not see the Earth moving downwards. Now, let's look at solution A. In solution A, we consider a different system. So now the system is only yourself. Because the system is only you, there is a force acting on you, and that is a gravitational force by the Earth. Hence, we cannot apply principle of conservation of momentum at all because there is a net external force acting on you, which is the system. Now, let's look at another concept. This is not in your notes. Let's see if you can explain it. Explain why a cannon recoil or move backwards when a cannonball is fired. So if we have a cannon, as it fire a cannonball, why does the cannon move backwards? Okay, we are supposed to state any assumptions, so let's start with the assumption. Assume external force such as friction are negligible. So there's no friction on the Earth, so this cannon is free to move backwards. Total momentum of the system, so we choose the system to be cannon and the cannonball. The momentum should be 0 before firing. It is at rest. When fired, the cannonball will gain momentum in a forward direction, and therefore, since there is no net external force, we can apply the principle of conservation of momentum. The cannon should move backwards since the cannonball moved forward, and the cannon will move backwards with an equal magnitude but in the opposite direction. Therefore, the total momentum after the firing is still 0. So before firing, momentum is 0. After firing, momentum is still 0. Therefore, there is no change in momentum, and the momentum is conserved. Okay, this is the end of this section. In the next section, we'll look at the types of interaction and collision and use that to solve momentum questions.